All right. Here we go. So question 18.4 asks us to draw the mechanism of the nitration of this interesting compound. So this would be what, 1,2,4,5 tetramethylbenzene, something like that. And the way that you do a nitration reaction is you treat the compound with a mixture of nitric acid and sulfuric acid. So we need both of those acids, and we know that sulfuric acid is about 10 million times stronger. And so that means that sulfuric acid is going to be able to protonate nitric acid. So let's start by drawing the mechanism of the formation of the nitronium ion. And so first we'll start by drawing the Lewis structure of nitric acid. So nitric acid looks something like this. So we put our Lewis structure of nitric acid, which looks like that. There we go. And then we have some sulfuric acid. So we have some sulfuric acid, and we'll draw the whole Lewis structure of sulfuric acid. A little bit painful to draw the whole thing, but let's just go over it once here. So what's going to happen is we're going to protonate here, and we're going to end up having the protonated form of nitric acid, which is going to look like this. So let me draw that. So now we have a positive charge on our nitrogen, and we have a positive charge on this oxygen next to it. And it's not very happy like that. And so water is going to leave. And when the water leaves, we form a new pi bond here. And I'm kind of running out of space, but I'll see if I can squeeze it in here. And so after loss of water, you end up forming this thing here, which is super electrophilic, and this is the nitronium ion. So nitronium ion. Now let's get to that nitration mechanism, and this is the electrophilic aromatic substitution mechanism, which is so important for students. So first thing we're going to do is we'll draw the aromatic ring, put in all 4 of our methyl groups, and let's put in our electrophile, our nitro. So I'll just draw it like this. So yeah, I need more space. There we go. So let's draw our nitro, or sorry, our nitronium ion. Looks like this. So again, this is a super powerful electrophile, and our aromatic ring is going to act as a nucleophile. So it's going to attack here, and then we're going to produce our sigma complex. So let's draw that with all 4 methyl groups here. Now we have our nitro installed on the ring. We have these 2 bonds intact, and here's our positive charge. And now we can draw all the resonance contributors to the sigma complex. So let's just get some practice in that. We can move this bond over here. I'm going to draw a little bit of an abridged version here, so I'm not going to draw the entire Lewis structure of the nitro. I'll just put that over here. And then that can happen again. We have another allylic carbocation, and so we can draw a 3rd resonance contributor. Still running out of space, so let's draw the 3rd resonance contributor. So this is our 3rd sigma complex. I guess all 3 of these resonance contributors count as the sigma complex. And here we go, like that. And in our last step, we're going to rip off this proton. Now, I didn't draw it here and here. You can put it in there if you want. But in the very last step, water is going to come in and behave as a base, and it's going to pull that proton off to restore aromaticity. So we have a water molecule, and it can just come along and rip that proton off, and we regenerate our double bond like that. And there you have it, folks. You have drawn the mechanism of an entire electrophilic aromatic substitution reaction. We had our nucleophilic attack. We have our sigma complex. And then we had our proton transfer. In the last step, we drew the product, and we even drew the mechanism for the formation of the nitronium ion. So that covers all of question 18.4. Any questions about the mechanism before we move on, because now we're going to get into Friedel-Crafts, which is similar. Got some, some nuances to it, like most things do in organic chemistry. But there we go. And so I expect my students to know the mechanism of electrophilic aromatic substitution. Very important mechanism. Well, let's take a look at our slides here. So I got to find out where I am. So somewhere around here. And this is where we left off. And so we just covered this mechanism right here. And now we're going to get into reactions to make intermediates 5 and 6. So the Friedel-Crafts reaction. So let's go back up in here and we'll find that part. We covered all this and we're here. Okay, so some new chemistry. And something I told you a while ago, or I've told you a few times, is that whenever you can find a way to make a carbon-carbon bond, it's reproducible, it's a good way to win a Nobel Prize. Well, as is my understanding, Friedel and Crafts didn't win a Nobel Prize for this reaction, but maybe they should have, because Friedel-Crafts alkylation involves the formation of a carbon-carbon bond between an aromatic ring and an alkyl group. So they found a way to make a carbon-carbon bond. So we take benzene, as is shown here, and we treat it with an alkyl halide as an electrophile, but an alkyl halide on its own is an electrophile. We know there's a dipole going this way, so we know that the carbon is partially positive, but it's not electrophilic enough to react with benzene, and thus we have to use aluminum chloride as a Lewis acid catalyst in order to get this reaction to work. And the catalyst, the aluminum chloride, functions as you would expect. It is a Lewis, it's a Lewis acid. And so our alkyl halide behaves as a Lewis base, an electron donor, and we end up making this complex, which undergoes a fragmentation to produce a carbocation. Well, if you have a carbocation in its solution, so let's imagine when you mix these two together, you end up producing a carbocation. Well, you can imagine that's very electrophilic, and the aromatic ring can attack that as a nucleophile. Well, let's check that out. And here's the mechanism. So once you form your carbocation, you get the nucleophilic attack, and you form a sigma complex. And as we just did, you should be able to draw all the different resonance contributors to that sigma complex. Then we have a proton transfer, the same proton transfer that we saw when we were doing halogenation, namely chlorination, when we used aluminum chloride, and you end up making the adding the alkyl group, and of course you end up regenerating the Lewis acid catalyst, and you form HCl. And in this case, they made butylbenzene is what they made in this case. All right, so that's a Friedel-Crafts alkylation reaction. Very cool chemistry, making a new carbon-carbon bond. I want you to go back into the recesses of your mind and think about carbocations for a second. What do we know about carbocation stability? If we're talking about carbocation stability, we know that a tertiary carbocation is most stable, followed by a secondary, followed by a primary, followed by methyl as being the least stable of all carbocations. And I want you to have that in the back of your mind as we look into this Friedel-Crafts alkylation in more detail. It says here on this slide that simple primary alkyl halides can be used. If you used ethyl chloride and aluminum trichloride, yes, you can make ethyl benzene, because if you think about, a primary carbocation, I mean, that's really unstable. And so instead of making, a primary carbocation like this, we say that probably doesn't happen. The electrophile that's presumed is actually the complex. So it's actually this whole thing. They presume that that is the electrophilic agent, but the bottom line is that you can add an ethyl group or a methyl group if you used methyl chloride. However, what if you had a longer chain, right? What if you had one chlorobutane, as is shown here? So this is one chlorobutane. Well, in that case, could you make a primary carbocation? pose not very much, because a primary carbocation, if we were to draw this, we know that's really, really unstable, super unstable. Unstable. And so what happens is that when you form the complex between the alkyl halide and the Lewis acid, you get the formation of the carbocation with a simultaneous hydride shift, which produces a secondary carbocation. And so if you try to do a Friedel-Crafts alkylation, so this would be a Friedel-Crafts alkylation, with a primary alkyl halide that has some kind of chain on it, you're going to end up with alkylation at the primary carbon, but you're also going to end up with alkylation at a position that results from a hydride shift that would produce a secondary carbocation. And in fact, you see you get this in an even higher yield. So you get a mixture. Now, you know, like you've seen this many times before, in organic chemistry, when we get mixtures, what do we want to do? We want to find a way to avoid getting mixtures. Nobody wants to get a mixture in organic chemistry. And what we're going to see is there is a way where you can make this compound, just this compound, in a very high yield. And so we're going to take a look at that in a little bit. But the bottom line is that when you do a Friedel-Crafts alkylation, if you have a primary alkyl halide, you've got to look out, because primary alkyl halides are susceptible to rearrangement. It could be a hydride shift, or it could be a methyl shift, and that's depending on the alkyl halide. So you'll see examples where there's methyl shifts that occur in the textbook. Well, you know, I always think of my students who love to remind me that, Mr. Dion, organic chemistry is the study of a bunch of rules. I agree, and the exceptions to those rules. And I agree with that too. If I was to say that wasn't true, I'd be full of baloney, okay? And there are 3 limitations that students have to be aware of to the Friedel-Crafts alkylation. And I'll try to provide you with a rationale for all 3 of them so that you're not just memorizing them out of thin air. The first one is your halogen as the leaving group, it's got to be attached to an sp3 hybridized carbon. Why can it not be attached to an sp2 hybridized carbon like here or here? Because we cannot have a carbocation on an sp2 hybridized carbon. If anybody ever draws this, if you ever have, you know, a friend studying organic chemistry and they draw something like this, that is a heresy. Okay, there is no such thing as an sp2 hybridized carbocation. So we can't have that, and thus that is why we can't have that reacting. In fact, I'm going to erase that. That's so ugly. Not going to happen. So that's your first limitation. Second limitation is that if you try to do an alkylation, so here they're adding a tert-butyl group, so they're using tert-butyl chloride and aluminum chloride. Looks good to me. But what happens is you would first get monoalkylation, okay? So you'd add your first alkyl group. You'd end up with this. Let me just move that out of the way a little bit. So you'd end up with tert-butyl benzene, and then it's going to react again, okay? Now, what happens is when you add that first alkyl group, this first tert-butyl group, it makes the ring more reactive. So this compound, tert-butyl benzene, is even more reactive than benzene. More reactive. It's even more ready to react than benzene. And if you're wondering, well, why the hell is that? Well, I'm going to cover that in a little bit. And so you could get polyalkylation, but here's the rub. Not the rub, but here's something that's really cool about our book, is that we will assume monoalkylation in chemistry 3111. So whenever we're looking at alkylation, we're just going to assume that it's monoalkylation. Don't worry about polyalkylation happening. It's just mentioned in the book. It can happen, and there's a good reason for it, and I'll explain it more when we talk about activating groups and deactivating groups. The last one is if you have a nitrobenzene, so if you have some kind of nitro group on your aromatic ring, Friedel-Crafts just doesn't work. Doesn't work at all. And the reason why is that the nitro group, and I know you all read the chapter before coming to class, so you'd know that a nitro group deactivates the ring. So deactivates aromatic ring toward substitution. So essentially, you put a nitro group on there, it just shuts the whole thing down. It's just making the ring just says, no, I'm not doing it. I'm not reacting. It's just too, I'm not reactive enough to react with an alkyl halide, even in the presence of a Lewis acid. With all that in mind, let's look at a question. And this is not a simple question. It's not really the most straightforward question in the book, but it's one of the first questions in this chapter. It says, predict the expected products when benzene is treated with each of the following alkyl halides in the presence of aluminum chloride. In each case, assume that you get monoalkylation. Actually, sorry, this is a pretty straightforward question. At least the first two parts are straightforward. The second part, we'll have to think about it a little bit. But the first part, for A, if we're just saying, okay, we're going to take benzene, and we're going to treat it with chlorocyclohexane. So this is our electrophile in the presence of aluminum chloride. Well, what's the intermediate that you're going to form? You would end up forming the cyclohexyl carbocation. Is that going to undergo a rearrangement? Could anybody answer that? Would that be a yes or a no? Would this undergo a rearrangement? And again, I would never try to trick you or fool you or something. Yeah. Thanks, Nick. I like your answer. Nick says nope, and whoever just unmuted their mic said no. And you're all 100% correct. So this is a good, nice question because it's not going to happen. And so, all that's going to happen is you're going to get aromatic ring, and you're going to have the cyclohexyl group attached to it. That's it. Done. Question is over. So now you've made cyclohexyl benzene. All right. I'm kind of running out of space here, so let's. I'm going to go to a blank document. Just nice to have space. Don't fence me in, right? So let's see here. So this is question 18.5. So this is 18.5B. So same thing. We're starting with benzene. And I'm pretty happy with the way you guys answered that question. So let's try this. What if you had tert-butyl chloride and aluminum chloride? What would be the carbocation that you would form? It would be this. So it'd be a tert-butyl carbocation. Will this undergo a rearrangement? Yay or nay? Anybody answer that? Yeah. I figured that my students would nail that one. Okay, I got one person saying no. Anybody else? If a vote on this one? I'm thinking that since it's tertiary, it's not going to undergo rearrangement, right? We've got a tertiary carbocation, therefore the answer is no. Thank you. Both of you are 100% correct. And so we're going to end up with tert-butyl benzene. Right? So far, Friedel-Crafts is a winner. All kinds of neat ways to add alkyl groups. Well, let's try one that's maybe a little more challenging. This is 18.5C. Now we're taking benzene, and we went to Walmart to the alkyl halide section, and we bought some of this alkyl halide. It was cheap. They were practically giving it away. Take this alkyl halide, please. Now, what would be the intermediate that you could form here? Well, this is a primary alkyl halide. And so are we going to get some of the primary carbocation? I mean, that's highly unstable. You might get some of this, but mostly what you're going to get is a hydride shift like this. And when this undergoes the hydride shift, so hydride shift, you're going to end up with, oops, what am I drawing? I'll try to draw it the same way it is here. You're going to end up with this, where we have a secondary carbocation. And so some of the nucleophilic attack will occur on this intermediate here. So that's a secondary carbocation. And there's probably some of it that would also occur from, let me draw the complex, because we don't like to draw primary carbocation. So some of it would occur from this complex as well, like this, where we have a positive charge over here. So that means my aromatic ring could attack here. or, you know, it probably can attack the complex like this too. Okay, it could probably do both of those things. And so we're going to end up with a mixture because we have both the complex and we have its rearranged form, right? And so the way that the book draws the rearrangement is different than what I have drawn here. Like they draw it where, let me just draw it the way they do it. So they say, okay, well, this is going to shift over here like this. Okay. So that's how they do it in the book. And that's probably more correct than what I showed here. I just find that students like this a little bit more. It's a little easier to understand and it gets the point across. But the bottom line is we're going to end up with a mixture. So we're going to end up forming some of this compound where we are attached directly to the primary carbon. So we have a methylene and then a methine, and then we have this. So we're going to get some of this product, but we're also going to get some of the product from attack at the secondary carbocation. So we have a geminal dimethyl like this. So I would say that this would be the major product. So this comes from the rearrangement, and then this would be the minor product, and this comes from the primary carbocation, if you will. Yeah, so we'll put primary here. We'll put rearrangement to the secondary carbocation. Give me a thumbs up if you follow me on that one, or just any questions about that one. Yeah, I know as an organic chemist and as an organic chemistry teacher and having taught a lot of students, I totally get it. That when you can have mixtures of compounds, it always gets more annoying. You're kind of, is it this? Is it that? But in the Friedel-Crafts, I mean, you know, even my brother who did a chemistry degree and then never used chemistry again after his graduation date, he said at least organic chemistry is logical. And so if you understand carbocation stability, students are usually able to rationalize to themselves, you know, this makes much more sense, that this is going to give me the major product. And sure, I'm going to have some of this, you know, which is going to give me some of the minor product as well. Not simple, is it? You know, but it's pretty neat. Friedel-Crafts alkylation. Well, now let's go back to our slides. And
Mr.
let's
Dion,
compare. Yeah, yeah.
I'm
Ask me
sorry,
anything.
I'm so sorry, just before you move on. So
No,
the
don't
major
worry about it.
the major product, I'm kind of confused how you got what you did because I would have thought that it was a tertiary, like you would have added it so it would be a tertiary at the end.
It
Well,
this
no,
is a
no, I mean
tertiary.
like at the what did you just say? I'm sorry.
This is a tertiary carbocation.
Yes, yeah. No, no, I absolutely know what you're saying, but the major product that you drew, I just wouldn't have thought that like the tertiary would be where you drew it. I thought that it would be at the end of the structure.
Well, if we let's just take a look at the carbocation itself. Okay, so let's just imagine that you could have this carbocation just floating out there in the ether. It's primary, it would be super duper unstable. But if this did exist, you'd have a hydrogen here, okay? So remember that if a carbocation rearrangement can occur, it will. And here we have something that's primary. So if we do a hydride shift, where we put the hydride over here, right? Because this carbon already has 1, 2 hydrogens attached to it. It's currently sp2 hybridized. Once you move that hydride in there with its pair of electrons, now you have 1, 2, 3. Now you've added a third hydrogen, so we have a methyl group here. And now this carbon is sp2 hybridized, so it has a positive charge. And thus you've gone from a primary carbocation to a tertiary carbocation. So there's no reason for this to rearrange any further. Are you with me on
Yeah.
that?
Yes, no, yeah,
Okay.
but
So
wouldn't it
now
add where that is though? That's what I'm trying to ask is like
it
you put it
it
on.
did. It
Oh.
did add this. So look, we draw in our double bonds like this. So look, here comes my nucleophile. It's going to attack here, right? So what is that going to look like? I'm going to have, I'll just draw it like this. I'm going to have my aromatic ring. Okay, let me draw it to the carbon that we had before just to make it similar. So I had the arrow, I think, attacking here to this carbon. Okay, so now we didn't touch either of those bonds. And the new bond that I made, I'll draw it in red. This is the new bond that I formed, right? What's attached to it? I have this carbon in blue. I've got these two carbons in green. Those are two methyl groups. So 1, 2. So that's one methyl. That's the other methyl. And then I have these two carbons in red. So I have 1, 2 coming off here. So this one and this one, right? So that would give me my sigma complex. And then after the loss of the hydrogen, so once you rip off the proton, then you're going to have the aromatic ring restored, and then you have this compound where you have the gem dimethyl and an ethyl. Does that make more sense?
Oh, yes. Okay. I'm so glad that I asked this. Thank you.
Yeah, no problem. No problem at all. Yeah, stop me at any time to ask me a question. I'm more than happy to answer it. But the bottom line is, Lindsay, are you with me that there's no reason for this to rearrange any further, right? Once it's
Oh yeah,
tertiary,
yeah.
okay, it's
Yes,
stuck.
for
So
sure.
it's just a matter of connecting the dots. And one thing that all organic chemists struggle with at one point or another is connecting carbons correctly. It's developing kind of an eagle eye to look at it and say, okay, well, it's connecting at this position. So I have two methyls, then I have kind of like an ethyl coming off of here like that. You would call that a neopentyl group, which is neither here nor there. You don't need to know that. But yeah, connecting the dots can be difficult. You know, you get mixed up on carbons and stuff. It's totally normal. So keeping track of carbons is a skill that all organic chemists are always working on. I'm sure there's people who are gifted at it, but good for them. All right, there we go. So we covered that one. Well, let's move on from alkylation to acylation. If you followed me on alkylation, my guess is that you're going to follow me on acylation. Good news. Same old thing. We're going to make a really powerful electrophile. We're going to have a nucleophilic attack. We're going to have a sigma complex. And then we're going to remove a proton to restore the aromatic ring and done. But now we're going to add an acyl group as opposed to an alkyl group. So check this out. Acylation, Friedel-Crafts acylation, is promoted by the same old Lewis acid, aluminum trichloride. Now, if you have something like this, I think that everybody knows that if I was to draw this, let me just draw the bond line structure like this. Everybody knows carboxylic acid. So carboxylic acid, it's one of the first functional groups that you looked at. Students love infrared spectra that have carboxylic acids. They're easy to recognize. If you replace the hydroxyl with a chlorine, so we have this. This functional group is called an acid chloride. Acid chloride. And you can see, that a Friedel-Crafts acylation involves aluminum trichloride as the Lewis acid. So you need to have a Lewis acid. And then you have an acid chloride. And when we do our chapter on carboxylic acids, we do a whole section just talking about acid chlorides, other things that they can be used for, why they're so reactive, blah, blah, blah. But that's something to look forward to on another day. Today, we're just talking about the acid chloride and how it can be used to affect an acylation. Well, you can imagine if you have 3 lone pairs of electrons on a chlorine and you have a Lewis acid, that the chlorine can act as a Lewis base, and the Lewis acid, of course, acts as a Lewis acid. Let's take a look at what that mechanism would look like. Check it out. Here's my Lewis base, my electron donor. Here's my Lewis acid, my electron acceptor. And check it out. You pour some electron density, you make a bond between the chlorine of the acid chloride and the aluminum, which breaks apart to form this Acilium ion that you have here. So here's another word. All kinds of new terminology in organic chemistry too. If you haven't noticed already, I'm always firing off the new terms. Like here's a new word, here's a new word. So you get the Acilium ion, and if we draw that Acilium ion out, Let me just draw it like this. Yeah, so here's your Acilium ion. What do you notice about the carbon? Does the carbon have a complete octet? The answer is no, it doesn't. But you can draw a resonance contributor. Check this out. You can draw a resonance contributor, which is going to contribute even more to the overall resonance hybrid. This would be the major contributor. Why? Because all atoms have a complete octet, right? The carbon here has an incomplete octet, but now the carbon has a complete octet. And so when I draw the Acilium ion, I don't draw it like this. And there's nothing wrong with drawing it that way. It's a resonance contributor. It counts. But Mr. Dion likes to draw it this way, just because I like everybody to have a nice, happy octet, as Bob Ross would call it. Well, let's take a look here. We form our Acilium ion. It's resonance stabilized, and because of that, it doesn't like to undergo rearrangement. I like the sound of that because I don't feel like dealing with a rearrangement at this moment in time. So let's take a look at what the acylation mechanism is. I would guess that if I had given you a blank sheet of paper and a pencil and said, what do you think the mechanism would look like? I think you would have said, well, let me draw the acilium. Here's your acilium ion. It's a really powerful electrophile. Step one, I have my nucleophilic attack. I form my sigma complex, or the uranium ion, whatever you want to call it. And then what happens in the end? I have my AlCl4 minus ion. That's going to abstract the proton. I also end up producing HCl, of course, and I regenerate my Lewis acid catalyst. So I end up with all three of these, and there you go. I've installed an acyl group. Is that neat or what? Installing an acyl group. Again, Friedel-Crafts didn't win a Nobel Prize. I wasn't part of the committee. They didn't ask me, so I don't know why, but anyhow, they didn't. Very neat chemistry, because what have you done? You made a new carbon-carbon bond. And whenever you make a new carbon-carbon bond, you're cool, at least the organic chemist. You remember that problem that we had where I said, okay, there's no good way to do this using Friedel-Crafts alkylation, because you would have ended up with this, plus we saw that we ended up with some of this compound, right? You ended up with a mixture during alkylation. Well, now I can teach you a way to be sneaky enough to just add a butyl group or any kind of straight chain on the end or on an aromatic ring. And it's a two-step process. The first step is just plain old Friedel-Crafts acylation. And then the next step is a brand new reaction. And this reaction is called the Clementine Reduction. And if you're wondering, what the heck is zinc with mercury in brackets? That's called a zinc-mercury amalgam. So this is a zinc-mercury. So let me just write here the word amalgam. Amalgam. And if you've ever worked in a dental office, you might have heard of an amalgam before. An amalgam is nothing more than they take zinc and the surface of it is coated with mercury. There's no mechanism for this in our textbook at all, but look what happens. You just go from a carbonyl and now you've just added 2 hydrogens. So it just burns it right off and you reduce it completely to an alkyl group or to a methylene. So you go from a ketone to a methylene, really, is what you're doing. And I just want to mention something. What are the names that we've looked at so far today? We saw Friedel-Crafts, and we saw Clementine, and yeah, those are the only names I can think of. Is there a name I'm missing today? No, I don't think so. So Friedel-Crafts, Clementine. Later on, we're going to learn a whole holy host of named reactions. I mean, they're named after people. We'll talk about something called the Wittig reaction. There's the Stork enamine synthesis. There's all these different things that are named after people. And let me just address this for you. Why do we like to name reactions after people? I can give you a really good reason why we use the scientists' names. It's because if you know what a Friedel-Crafts or a Clementine is, if I see you in the hall, let's say you're a chemist and I'm a chemist, and we meet in the hallway, and I say, hey, McCall, did you try a Clementine reduction? That means that McCall would understand exactly what I'm talking about. You know, a scientist would say, okay, Clementine reduction, yeah, treat it with zinc, mercury, amalgam. Instead of me saying, hey, Nick, could you try treating it with a zinc and a mercury amalgam with HCl, and then you cook it up? You know, it's so much faster to communicate with people if they just say, do a Friedel-Crafts, you know, do a Wittig, do, you know, the Chichi-Babin reaction. That's a great name, you know, the Chichi-Babin reaction. It's something we don't cover, but there's a whole book of named reactions in organic chemistry. And again, it's just such a fast way to communicate with another scientist. You just give them a name, they'll know. And it's just, you know, organic chemists are like everybody else. We like to get the maximum amount of work done for the minimum amount of effort. All right, so Clementine reduction. So let's go over the Clementine reduction. You have the zinc mercury amalgam. You need some hydrochloric acid, and you heat that up, probably to reflux, which just means you boil it, you know, for an extended period of time, and you remove the carbonyl. And the thing is it says that here that for the Friedel-Crafts acylation, polyacylation is generally not observed. Remember how I told you if you added an alkyl group, like a tert-butyl group, that it would keep adding and adding? Well, if you add an acyl group, it usually doesn't keep going. And the reason why is because the acyl group is deactivating. So um, it, I'll just leave it like that. But it renders the aromatic ring less reactive. I see what somebody typed in the chat. They said, sounds like chemists use nomenclature for conversation. They absolutely do. They absolutely do. I freely admit that. Okay, well, let's move on. Let's try one more practice problem here, and then we'll take another short break. Let's see, just thinking out loud here. Okay, let's take a look at this question. It says, identify whether each of the compounds can be made using a direct Friedel-Crafts alkylation, or whether it's necessary to perform an acylation followed by a Clementine reduction to avoid a carbocation rearrangement. Well, you want to make a bond between the carbon on the aromatic ring and the carbon in the alkyl group. So what would your alkyl halide look like if you wanted to do a Friedel-Crafts alkylation? It would look like this. We'd have all of these carbons, and then you'd have to have a halogen. Let's pick chlorine, like that. Well, my question to you is, you know, if this made a carbocation like this, would this undergo a rearrangement? Yes or no? Could anybody tell me? If you made a complex, oh, absolutely. Absolutely, wouldn't it? That'd be nasty. You'd end up with a total mixture, wouldn't you? Because this would rearrange to give you, you know, then you'd have this where you have, you know, a carbocation here, and now you'd end up with the tertiary carbocation. And so if you were to try to do that reaction, jeepers, I'm running out of space here. But if you took this, if you took benzene and then you treated it with this alkyl halide and aluminum chloride, you'd end up with a mixture. You'd end up with some of the desired product, so pencil that in here. But the major product that you would end up with, right, Lindsay, would be the reaction with this electrophile, which would give you what? Let's draw it out carefully here. You have your aromatic ring. I'm going to move it out of the way just slightly here. So look, here's this carbon that I have highlighted. Maybe I'll use my green pen. Here's this carbon. So you have a bond to that green carbon, and what's attached to it? You're going to have two methyl groups, and then you'd have this. So this would be your major product. And that's not going to work. I mean, sure, you get a rearrangement, you get some of the product, but that seems like a pretty crappy way to make it. So let's go over to a blank document, and we can't do this without drawing something pretty. So let's draw a pretty reaction here. What would that look like? What I think would be a better strategy, so this is 18.8A. The strategy you would want to take would be to take benzene and then treat it with the acid chloride, like this. Okay, so AlCl3, and that's going to give you the acylation product. So you end up with this ketone, like this, and then you can do the Clementine reduction. So you treat that with the zinc mercury amalgam, some HCl, and you cook that up, and you end up with the product is the only thing that you get. So that would be the way to go. All right, I'm probably going into way too much detail here. Let's try the next one, 18.8b. Let's give this one the old college try. 18.8b, they're asking you, could you make this compound, solely by a Friedel-Crafts alkylation? So this compound here, could anybody answer that? Would you want to use alkylation or acylation followed by a Clementine reduction? Anybody have an idea about this one? 18.8b.
Should use acylation followed by the Clementine reduction because you would have some rearrangement.
Oh, big time, wouldn't you? Yeah, I couldn't agree more. Let's take a looky. Look, if you go do a retrosynthesis and said, okay, well, I want to add these 3 carbons. So here's this carbon. That means I'd have to have a halogen attached here. So let me just spruce that up a little bit. Like, oops, son of a gun. There we go. Well, if that was your carbocation, I mean, that's primary. That's definitely going to undergo a hydride shift to give you a tertiary carbocation. What that means is if you were to try to do, and I'm just going to go a little bit faster now, if you took benzene and you took it and you treated it with this compound, which is isobutyl chloride, it's getting too late in the day here, you'd end up with a mixture. You'd end up with some of the desired product, but you'd also end up with tert-butyl chloride, right? Because it would attack here, which would give you tert-butyl chloride. So you end up with a mixture. And so what Caitlin is saying, she said, look, there's a much better way to do this. Why don't you use the acid chloride instead of this? So she said, put a carbonyl on it right here. And then if you have a carbonyl there, so let me just redo everything. If we have a carbonyl on there, then you have the acid chloride, like this, aluminum chloride. We end up making a ketone. So here's the ketone that you would end up with. And then we're going to do a Clementine reduction. So for that, you need the zinc mercury amalgam, HCl, and heat. And that's going to give you the alkyl group. I'm getting sloppy with my lines here. Here we go. And you end up with isobutylbenzene. Looks good to me. All right, so let's go back to our slides and take a look and see what we've covered today. We're getting to our 3rd hour of class today. So let's see, what have we covered? We have covered today. Let's just review here. I'll use my yellow highlighter. We talked about iodination, which is discussed in question 18.1. We covered bromination, chlorination, nitration, sulfonation, desulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation. We covered the Clementine reduction, and we covered reduction of a nitro group. So reduction of a nitro. These are all the things that we have covered today. And I think that's enough information for one lecture. And so on Friday, what we're going to do is we will talk about a little bit more about substituents on an aromatic ring. So just as a preview, we go back all the way back here, and maybe you don't want a preview, I don't know. But we're going to get into section 18.7 and 18.8, where we discuss what are called activating groups. So that's covered in section 18.7. Then if you go to section 18.8, we get into what are called deactivating groups. And you have to have a solid understanding and knowledge of what makes a deactivating group and what makes an activating group. And that is all summarized in this table right here. Now, I can't remember exactly which table it is in the book, but it's covered in section 18.10. Students have to memorize strong activators, moderate activators, weak activators. Then they have to memorize strong deactivators, moderate deactivators, and weak deactivators. Now, the good news is that, the whole idea of something being a strong, moderate, or weak activator or deactivator, it's organic chemistry. So I'm going to provide a rationale for you. But if you want to get a head start on Friday's lecture, what I would recommend at the very least is reading the remainder of the chapter and taking a good hard look at table 18.1 and see if you can understand the rationale behind everything in this table, because once we go over the entire table, then we're going to talk about, the directing effects of substituents on aromatic rings. And then we're going to look at what would happen if you had more than one substituent on an aromatic ring. And then you can imagine after all that, we get into, where is it? Section 18.12, synthesis. And we're going to see all kinds of different syntheses that we can do. So there's a lot of synthesis in this chapter. But again, what's the first step to mastering synthesis of anything is having a firm grasp of all the reactions in the chapter.